Computers are just a bunch of ones and zeros and hardware that crunches those ones and zeros into other ones and zeros. We, the humans, are the ones that decide what those ones and zeros mean. This is a number, this is a string of text, this is a picture, this is whatever. Usually the only time we have to put computation into human form, as in the computer uses base 2 because ones and zeros, and we use base 10 decimal. The only time we really need to have something in base 10 is when we're reading from the user or outputting to the user. Otherwise, it just stays in whatever format the computer uses. Computers nowadays universally have an 8-bit byte, as in you have 8 bits, 8 ones and zeros, and you combine bytes to make larger things, but the byte is really the unit we think of. We measure files in bytes, kilobytes, megabytes, and so forth. So if this is a signed number, it can store -128 to 127. Unsigned, it can store 0 to 255. But what if you're only worried about storing decimal digits? 0 through 9. 0 through 9. Well, if you can store 256 digits and you're storing 10, that's pretty wasteful. What is the smallest we can get away with? Well, obviously unsigned, because a digit doesn't have the capability to be negative. You don't have negative digits. So we do unsigned. Well, 1 bit can store 2, 4, 8, 16. So if we use 4 bits, we can store 16 digits. We only have 10, so that's still wasteful, but, there you go. And, as a benefit, you can put 2 of them in 1 byte. So binary coded decimal uses 4 bits, 4-bit halves, also called nibbles sometimes, NYBBLE, in this format, to represent decimal digits. Bonus, 4 bits is also a hexadecimal base 16. So this is 1 hex digit, this is another hex digit, so together, 2 hex digits make a byte. So let's say we have 2 in here, and let's say we have 4 in here. So this would be 24. These 4 bytes would be the digit 2, these 4 bytes would be the digit 4. Don't worry about which order it's in, that's just a computational detail. We'll just write it like this. However you write it, however you compute it, depends on your software. Well, in hexadecimal, that's 24. Now, the actual hexadecimal, if you take this together, is 2 times 16 plus 4 is 36. But we're not doing that. We're not using the full range of 16. We're not actually having a number here, we're having digits. So the side benefit is you have 0 through 9 as your decimal digits and 0 through 9 as your hexadecimal digits. So hexadecimal, write it out, it's the same as whatever number it is. That's pretty cool. That's pretty handy. And that's literally all BCD is. Binary coded decimal is just using 4 bits at a time to represent a decimal digit, and you keep it in that format. Instead of using a base 2 number of however many bits, you have base 10, and you have to do your math as base 10. And obviously, a computer doesn't work like this. A computer doesn't work on 4 bits in this way and that. So you have to hand code all of the software to actually write in BCD. Although, old computers that actually used BCD natively, of course, had it in their CPUs or firmware or whatever. But nowadays, you'd have special software to do it. One reason to use BCD is when you want to actually do math directly in base 10. Because usually, all you care about is having the most accurate, let's say you're making fractions, doing fractional computation. You want to take the absolute maximum precision you can all the way through the computation. Keep every single digit your computer has available, compute, and at the end of everything, you round off if you need to. And that way, the computer keeps rounding the whole time, but it's rounding way at the end so that you have precision, maximum precision, until the very last step. But what if you're doing financial calculations? People have been doing financial calculations, dollars and cents and whatever, in base 10 forever, since there has been currency, long before computers were a thing at all. And sometimes you don't get the same answer when you're doing decimal versus just keeping your maximum precision and then rounding, because banks, financial institutions, your point of sale, whatever, there might be points at which it rounds, and it rounds on base 10, and you're going to get, pennies off, and for a bank that does 1 billion transactions a year, that's going to be a lot of pennies. So you might use BCD to do direct base 10 math, and so that you can implement your algorithms to do the rounding the same places where a human by hand would have done the rounding, traditionally. And so you get the same answer. a technically less accurate answer. Nowadays, we don't do that. Programming languages and libraries have code in there to do this stuff. C#, for example, has the decimal class. So nowadays, we just use software to do it. We don't use BCD anymore for that, but you could. Now, the big thing you'd still use BCD for nowadays is if you're making a simple device that's using, your 8-segment display where you've got this to make your digit, maybe a decimal point or whatever, like a good old calculator. I guess nowadays you'd have LCDs, you'd have OLED displays, you'd have fancy displays. But if you are using, like I would, these simple things, you want to make a simple device, then you have a chip, a very handy simple chip that decodes from BCD to which LED segments are to be lit. So you have 4 bits, 4 inputs into the decoder, and the output is however many pins. For example, 9. It might be, a common cathode and then 8 pins for each LED. This is basically demultiplexing. So you only need 4 pins to input a BCD into this decoder, and it already knows, here's your 8 pins, hook them up to your LEDs. So it's space inefficient, but it's computationally easy. You spend some space to just do things easier. And you can have a register. You could have, a 4-bit or 8-bit register, and you write to it, and that's plugged into your decoder, which is plugged into your display. So anytime you want to change the digit, you just need, let's say, 4 pins to write the value, and then a couple other pins to decide which register you're writing to, and you set a digit. And then it just stays there. You got some flip-flops in there, and it just stays there displaying that digit. So that's how you do a calculator. So that's what I consider the only valid use for BCD nowadays, unless you're working with old hardware that used BCD, retro stuff. But there's one other thing to mention. We have 16 different codes. We obviously use 0 through 9, so we have 6 left over. Let's say you have a display that can do other things. Let's say you can display a decimal point, so you could have a code that displays a decimal point. Maybe it can display a negative, to say negation. If you're doing scientific notation, 6.2 E10 or whatever, you could have an E. You could have whatever. You can use these other codes for something. And if you have that decoder chip might use all 16 codes. So it's just an option. It doesn't have to be completely wasteful. If you're making a display, you could have that display do 6 other characters in addition to your digits, should you want. But that's it. BCD is the simplest thing in the world. It's just 4 bits store a decimal digit. Instead of treating the bits as a base 2 number, it's just a container where you store a base 10 digit, and you do the math in positional notation, essentially. Couldn't be simpler. So while you marvel at how far display technology has come in just a few short decades, I'll be seeing you.